This problem here, once it comes to the surface charge, right, we want to know what is, let's say, if I have a parallel plate like this, if I want to find the electric field between the two parallel plates, how do I go about finding it? I need to know what is the surface charge density here. Once I know what is the rho s, then I will be able to figure out what the electric field in between them is. So the next is for you to appreciate how do you end up getting an expression for the electric field. Given a certain surface charge density, in this case, it's a line charge density, what is going to be the electric field? How do you go about finding it? Imagine you want to find there is a certain rho L, a line charge density that is in the form of a ring, like a hula hoop. You want to find what is the electric field at this point P. Let's call that point P, the coordinate is 0, 0, Z. I want to find the electric field at 0, 0, Z. Since the point is 0, 0, Z, I want to find the electric field at this location. The position vector of that is going to be Z times Z hat, isn't it? All this question is, what is the electric field at that position? What is the electric field at that position where this is Z, Z hat, any point along the Z axis? Now I know that it is this many coulombs per meter. And if you were to read the question carefully, you will see that it is a uniform, it says uniform charge density. Uniform is the key word there. So what do we mean by, and it's lying in the XY plane and the total charge is Q. And the total charge is Q. So that means by uniform, we mean that, imagine this hula hoop is there, yeah? If the radius is R, what is the length of this loop? 2 pi R. So the entire length is 2 pi R, right? Capital R. Imagine you go and cut this loop and make it like a straight line. Make it like a strip. It will form a straight line like this. The length of this line is going to be 2 pi R. Now, when I say the charge density rho L is uniform, that means this rho L is all having the same height, which is rho L. It is uniform, yeah? Meaning that at this location, whatever charge that you see is exactly the same charge that you see at this location. It's the exact same charge you see here, the exact same charge. It's all the same. It's not, at some places it's high, at some places it's low. It's not like that. It's always the same. I want to find what is this dq. How do I know dq? Dq is rho L dl, isn't it? dq is rho L dl. But how do I know what is dl for this guy? If I were to take the small little angle here and zoom it in, I see a R, I see a d phi. So what is the length of this arc? This R d phi. So this R d phi is my dl. So that means my dq is rho L dl, which is going to be rho L R d phi. Right? Where this is coulomb per meter and this guy is in meters. When you multiply, you get the charge, a small little charge dq. So now you know dq, you know what is dq. Now what's the location of dq? What's the location of dq? We know what is the location of R, but what's the location of dq? If I were to see this with my eyes looking down the x-axis, if I were to view it like this, z-axis, what I will see is the x vector like this and the y vector like this. What shape will I see? I'm going to see a circle like this. This is R, this is phi. What will be the x coordinate of dq? If this is R and this is phi, so what is the x coordinate? What will be the y coordinate? R cos phi and R sin phi. This becomes my source, right? This is my destination. So destination is R. I call my source to be my RP, right? I want to find the position vector of RP. I need to know my XP, YP, and ZP. So this is my X and this is my Y. Do you know that my source is at the location of R cosine phi and R sine phi, and my Z is going to be 0. This is my point P, the source point. The source point is at R cosine phi, R sine phi, and 0, which means my RP is going to be R cosine phi in the X hat plus R sine phi in the Y hat. So you know your destination, you know your source, you know how much is the source, you also know how much is the source. Then all that you need to do is simply find the small little electric field due to that source, isn't it? So what is that small little source? Because it's going to be 1 over 4 pi epsilon naught all the time. The dq r minus rp is destination minus the source over destination minus the source, the whole cube. So what we are doing now is, we know rp, we know r. So I'm going to simply substitute that. We know this rho L r d phi here. Now the key thing is the total charge that you have, right? The total charge is given as Q. Total charge is capital Q. I'll call this S. It should not be P. Yeah? So I call it S because P is already taken here. I call this point S. So this is going to be S. So this is going to be S. S is the location of the source. If you see the location of the source on this diagram, you know that the X location is R cosine phi and the Y location is R sine phi. So it's R minus RS, destination minus the source. This point is S. Origin is here. S is this point where the source is, the source charges. P is the destination. S is the source. dq is at the location S. Now the total charge is Q, right? We know that this total charge is the line integral of dl rho L dl over the entire length. dl is r d phi. dl is r d phi. So this is going to be 0 to 2 pi, which makes it, if I do the integration over d phi, 0 to 2 pi, it's going to be 2 pi r rho L, which is exactly the same as the area of this strip, which is exactly the same as the area of this strip, where this is the length and this is the height. Length and height. So from here, you notice that your rho L is going to be Q over 2 pi R. This many coulombs per meter. You just figured out the line density. Now I can continue to say my dq is rho L R d phi over 4 pi epsilon naught R minus Rs over R minus Rs, the whole cube. So now comes the interesting part. What is R minus Rs, the whole cube? If I were to take R minus Rs, my R is just simply ZZ hat minus Rs is going to be R cosine phi in the X hat minus R sine phi in the Y hat. What will be R minus Rs, the magnitude of it? The magnitude of R minus Rs is going to be Z square plus minus R cosine phi, the whole square, plus minus R sine phi, the whole square. The Z square, Z component square plus X component square plus Y component square. This is going to be z square plus r square. If you were to see this picture here, right, this length, this r is going to be z square plus r square, square root of z square plus r square, because this makes a right angle system. Yeah, Pythagoras theorem kicks in. This is right angle, z square plus r square, square root of that is going to be the hypotenuse, right, r, the distance between the source and the destination. So you got all the three parameters to substitute in here to get my dE. My dE is going to be rho L is Q over 2 pi r, but let me maintain it as rho L for the time being. R d phi over 4 pi epsilon naught square root of z square plus r square, the whole cube. This is the whole cube times this entire term, the r minus rs. This entire term has to come in, the r minus rs term, which is becoming z hat minus r cosine phi x hat minus r sine phi y hat. This is the electric field, the small little electric field due to the small little charge at this location of Rs, at this location of Rs. Now, if you notice, then how do I find out the complete electric field? Then I need to integrate it over d phi. This is the small little dE over the d phi. So the total electric field is going to be the integral of this whole thing, where in terms of d phi, so that means any term that does not depend on phi, I can take it out. That means rho L r over 4 pi epsilon naught square root of z square plus r square, the whole cube, and this integral d phi, right? Notice that that d phi multiplies this d phi multiplies this d phi multiplies this. There are three terms in the integral, right? So if I were to do just the integral alone, it's going to be z in the z hat direction, d phi 0 to 2 pi, minus in the x hat direction, this term here, which is r cosine phi d phi 0 to 2 pi, minus y hat, which is this term here, r sine phi d phi 0 to 2 pi. Turns out that when you integrate cosine phi from 0 to 2 pi, this whole term is 0, because cosine phi, right? If you look at the picture of cosine phi from 0 to 2 pi, the plus and the minus cancel each other, and this integral is 0. Similarly, here this term goes off to 0. Only term that is left is this guy, and this integral is rather straightforward, z 2 pi. So when you go ahead and do that integration here, this becomes rho L r over, this becomes 2 pi z times 2 pi z. In the z hat direction, the z hat remains, the x hat, y hat becomes 0, 4 pi epsilon naught square root of z square plus r square, the whole cube. Remember the rho L that we had initially, the rho L was Q over 2 pi R. That many coulombs per meter. So if I substitute that rho L in here, this 2 pi R and 2 pi R cancels each other. So I will have simply QZ over 4 pi epsilon naught square root of z square plus r square, the whole to the power 3 in the z hat direction. This many volts per meter. This is what mathematically it turns out to be. As you can see, the electric field is only in the z hat direction. The electric field is only in the z hat direction, meaning the electric field due to this guy is like this. The electric field due to this guy is like this. So when I vectorially combine this and this, right, I end up getting a vector only in the z direction. That means two diametrically opposite source points, two diametrically opposite source points lead to two electric fields that combine and add to each other to give only z component. The x and the y cancel each other. So the resultant electric field is going to be only in the z hat direction. This is the destination point. This is the source point. Yeah, I call the source point Q here. So when we do that, you get r minus rq, which is this guy. Then r minus rq, the magnitude is going to be r square minus z square. That's what I said, that if this is 90 degrees, this is one length of the rectangle, this is the other length of the rectangle, this is going to be square root of r square plus z square. Pythagoras, simple Pythagoras theorem, right? The dq is r dθ. How did we get this? Because we wanted to know that r dθ, this dq is going to be simply, if I have this to be my dθ, and this is length r, the length of this is going to be r dθ. So this is going to be r dθ times rho l is going to be that unit dq that we are looking at. So the small little electric field due to small little dq is going to be of this form. You have three terms, but fortunately this term goes to 0 and this term goes to 0 when you do the full integration to 0 to 2 pi. This whole term goes to 0. And this whole term goes to 0. So you're left only with the z component. And that turns out to be this nice little expression here.